Return, so that's wonderful. So now, after giving that very brief and concise presentation before, I'll hand out the exam notes, see what you remember. But anyway, what I'd like to talk to you about is how we protect the aquatic ecosystems in Australia from individual chemicals and from mixtures, and run through how we're applying that to protecting the Great Barrier Reef. So in Australia, we have, a bit like your Water Framework Directive, we have an overarching document, which is our National Water Quality Management Strategy. And it's trying to govern all aspects and manage all aspects of water quality. Just one of those many documents is the Australian and New Zealand Water Quality Guidelines. And the purpose of that is to protect our waters for a whole variety of different uses: human, ecosystem, recreation, aesthetics, irrigation, etc. And importantly for us, cultural. We have an Indigenous population and they have some strong religious and cultural beliefs associated with water. So it's important for us to include that. The way we protect our waterways is by deriving numerical limits, which we call guideline values. And for people who know anything about the guidelines from Australia and New Zealand before, they used to be called trigger values, and we've moved away from that term now. So how do we actually do that? Don't worry about all the boxes. The key points I want to make here are simply that we use two separate methods: the SSD, Species Sensitivity Distribution method, and the Deterministic Assessment Factor method. We always, if we have sufficient data, use the SSD method in preference. We only use the assessment factor method if we have insufficient data. So our preference is always to use the SSD. The actual methodology is very, very similar to what you're used to here in Europe and the States. There are some subtle differences, but by and large, if you read the document, you'd understand it and be very familiar with it. So, I'm already losing people. Jeez. 2 slides and I've lost someone. I've got 24 slides. So feel free. Look, there's 12 more of you who can just disappear through the talk. You know.
Just in the wrong room.
Yes, of course. Yeah. So when it comes to the SSD, we use the Berlioz 2 type software to fit the distribution to the data. We use that because it's a more flexible approach. It selects from a family of distributions, which are called the Burr Type 3 family of distributions, and they have approximations for a lot of the other distributions that some of the other software programs use. We have a range of different levels of protection that are provided, depending on the type of water body and its current status. So for high conservation values, such as waters in national parks or marine preserves, we offer we're aiming to protect at least 99% of species. For most waterways, they're low to moderately modified, so we're aiming to protect at least 95% of species. And in highly modified systems, such as streams which have going through a large industrial area, obviously they're quite heavily contaminated, the level of protection is lower, but our goal is always to move them over time up to this standard level of protection. So just to make it clear, we use the terms PC because we like to emphasise what we're protecting, rather than the HE, which sort of emphasises to us what can be permitted to be harmed. So your HC1 is the equivalent of our PC99, okay? It's just 100 minus the other value. So because we're in Sweden and I'm trying to learn new languages, I'm going to say these numbers, or I'm going to try and say these numbers in Swedish, so please don't laugh too much. So there are 3 important points about our guidelines which are different to some of the others. The first point, is the guidelines are not pass or fail. It's not pass or fail system. Svol, they provide guidance only. And trea, they have no legal standing. Okay, so they are somewhat different to your EQSs here in Europe. So how do we actually implement them, these guideline values? So it's basically there's 2 sort of, one decision point and 2 outcomes. And this is what we do for individual chemicals. I'll come on to mixtures in a minute. So if the concentration of an individual chemical is less than the guideline value, we interpret that there's a low probability of unacceptable environmental harm, and no further action is required. If the concentration is greater than the guideline value, we interpret that there's a moderate to high probability of unacceptable environmental harm, and therefore further action is required or triggered. And Yaroslav, you'd sort of appreciate that. So what that means is the terminology we use is you can conduct a site-specific investigation. So you might be looking at the bioavailability, if it's an organic, the speciation if it's a metal. You might be looking at the relevance of the species that were used to derive the guideline value compared to what you've got. You might be looking at the physicochemical properties of the water body that you're investigating. Or, of course, you can start some remedial management action. So you have some options. In terms of mixtures, generally we don't derive guideline values for mixtures, but in terms of the implementation, we do consider mixtures. So this is the current version of what we do, which was published in 2000. And we say that if you have a mixture, you assume there is concentration addition unless there's clear evidence of synergism, okay? And, it's the same old toxic unit approach. That's for the toxic units for an individual chemical. We divide it by our guideline value, and then you can sum those up for all the chemicals in your mixture. Certainly in discussion group 3, we've very clearly discussed what some of those limitations are of this method, and I'm sure you're all aware of those anyway. So again, how we actually deal with mixtures in terms of our system, again, it's in reference to our guideline value. If the sum of the toxic units for the mixture is less than 1, again, a low probability of unacceptable environmental harm and no further action is required. If any, if any toxic unit or the TU mix is greater than 1, then we're in the situation where we think there is a moderate to high probability of unacceptable harm and further action is required. So that's how we deal with it. That's the overall situation is not going to change. We are currently revising our water quality guidelines, and what I'd now like to do is talk a bit more about those, the revision, and how we're implementing that in terms of protecting the reef. So currently we have water quality guidelines for about 250 chemicals. We are revising the whole guidelines. We've refined our method. If anyone wants a copy of the new methodology for deriving our guideline values, just let me know and I can provide that to you. As part of the official revision, we're deriving guideline values for 30 new chemicals. They're either in fresh or marine environments, and those chemicals were identified by consulting various stakeholders, such as the various state and federal environment protection agencies, primary industry departments, and those sorts of organisations, and also NGOs. But in addition, from the official set which are being derived, the Queensland government, where I was working, is actually deriving guideline values in fresh and marine waters for another 24 pesticides. The pesticides that we're deriving guideline values for are here, and you may ask why. Why on earth are you doing this? Well, there are a couple of reasons for that. First of all these pesticides are currently licensed for use in Australia. Some of those chemicals may surprise you that they're still in use in Australia compared to some countries, but nonetheless they are, and that's not my decision. But more importantly, we are monitoring and finding these chemicals in our waterways. And Australia has a number of very unique and highly, politically sensitive ecosystems that we feel that we must protect. And one of those is the Great Barrier Reef. This is the world's largest reef system. For those of you who don't sort of really know Australia, that's Australia there. The Great Barrier Reef, the green here is the same as the green down here. And basically that's the land which is adjacent to the Great Barrier Reef, okay? Brisbane is just there. So it runs for about 2,500 kilometres along the coast, and it's a World Heritage Area. And so it's very much on the international radar. This is how we all like to think of reefs. Picture perfect. You go along, you see fabulous fish, corals, etc., and it's just all romantic and all those sorts of things. It's just gorgeous. That's the image we all have. Bit like I think of that like the Danube. You might have a slightly different impression. Because we have the ads for the great big cruise liners going down the Danube, and it's always beautiful blue water. And it's like, oh, look at that. You probably have the same sort of thing. But the reality... Oh, sorry, I've skipped ahead. As we say in Queensland, when they're promoting it, beautiful one day, perfect the next. And when it's like that, you have to agree. But the reality is a tad different. It's like any other system, any other ecosystem. There are multiple stresses acting upon it. And these are just some of them. It's got huge amounts of cattle grazing, quite substantial amounts of gully erosion, commercial and recreational fishing, commercial fishing, exporting and importing all these sorts of various goods, some very serious mines in Queensland, quite vast amounts of sugarcane and intensive horticulture, urban development, and the waterways which drain the land and transport contaminants out to the reef. We also have what we call cyclones. Other people might call them tornadoes or hurricanes. There, as you can see, this is the map. That's about 2,500 kilometres, that bit here we see. This is a big mama. That's a big cyclone coming towards us. We also have the crown of thorns, which is a starfish, and it basically treats coral like a smorgasbord. It just devours it. And we have coral bleaching, which is related to elevated temperatures, surface water temperatures, and that is a natural phenomena, and it's related to the El Nino, La Nina of climatic events. But climate change is disturbing that and changing the frequency in which Australia gets the hot climatic conditions which lead to coral bleaching. So I think you've got the picture now. There are multiple stresses there. In addition to just the rivers which are discharging, obviously the land in the catchment has a whole variety of different uses. And some of the contaminants which are being transported out constantly through those rivers can be seen here. You've got eroded soil, a whole range of pesticides, metals, nutrients, road runoff, industrial chemicals, sewage discharges, etc. So they clearly are complex mixtures. And these parts of Australia, some are very dry, we call them dry tropics, and some of them are wet tropics, and they can get 3 to 5 metres of rain in 6 months. So when it rains, it rains. So in the early 90s, there was a big review of all the known information about the science and of what was adversely affecting the reef. And they clearly identified a range of different factors, shown here. This is just some of them. And it was identified that water quality was a key issue that the Queensland government, that's the state government that owns all the land next to the reef, and the Australian government, that they could in fact make a significant difference to the water quality. And so they developed the Reef Water Quality Protection Plan. But obviously that's only dealing with the water quality issue. And so more recently they've developed again this overarching 2050 Reef Long-Term Sustainability Plan to deal with all the multiple stresses that are affecting the reef. And that has very much been brought about, thank you UNESCO, because of international pressure. The UNESCO was not happy with the adequacy of the Australian government and Queensland government's approach, and they put a lot of pressure on. So it's really good sometimes to have international critique of what you're doing. Politicians didn't think that. So the Reef Water Quality Plan, it has 3 key components. Because we're trying to deal with the water quality, we call them paddocks, farmland. That's our agricultural land. So you have to be addressing the land management. Oh, I'm sorry, step back. This is our no environmental harm, what's it? Non-toxic environment. This is our non-toxic goal. This is the goal for the Reef Water Quality Protection Plan. By 2020, amazing, we similarly have the same dates. Something's happening there. The water entering the reef should have no detrimental impact on the health and the resilience of the reef. Okay, so we've got the same goal here. We call this an aspirational goal. We know full well that we are not going to achieve that by 2020. Nonetheless, we are putting that goal out and we are striving and making every effort to get towards it. If you don't have a longer term goal, it's easy just to sort of rest on your laurels. We've got this out and we're really trying to drive forwards. In order to achieve that, we have to change how we are managing the agricultural and all the other types of land uses. So we've set a range of land management targets, and I won't go into those. Suffice to say, the logic is if we improve the way that we're managing the land, the agricultural land, mines, etc., that will improve water quality. There will be less contaminants in that water going out to the reef. We have specific targets set to decrease the loads, man-made loads, very importantly, man-made loads. So loads is just the mass. Is it kilograms of sediment going out or kilotons, etc.? Again, the logic being if we improve the management there, it will improve the water quality, and that in turn will allow us to make progress towards achieving that goal. So in terms of pesticides, the target is to reduce the pesticide load by 60%. So to reduce the total amount of pesticides going out to the reef by 60%. It's quite an ambitious goal. But we're all ecotoxicologists or related to that. We know, understand these things. We all know that loads are toxicologically completely meaningless. The total mass doesn't really help us. So my group has been arguing that we need to have something which takes into account concentration and the duration of the exposure, because that's what's really important. But nonetheless, we started from a base of having loads. We have argued that meeting the target will not necessarily give us a commensurate decrease in the toxicity of the waters. And that's what we're ultimately about, if you think back to the goal, no environmental harm, okay? We also argued that the loads could actually misdirect the management activity in terms of how we're trying to reach this target. And I'll give you an example of that in a minute. So, given that we've been critical of the current loads, that's all very easy to do. It's nice to criticise, but they always say, well, show us what else you could do. So what we have done is we have, as an interim step, because it's hard, as in discussion group 3, we had this thing, it's hard to go from one thing to a completely new system. So we heard that message loud and clear, and so we've developed a toxicity-based loads, where we are converting the loads of the individual pesticides to a diuron equivalent in kilograms. And we're doing this for 5 PS2 herbicides, which are the key pesticides we're concerned with. So in terms of when we've done that, our target will then be, rather than a reduction of the total load, it's the reduction of the toxic load of our diuron equivalents. But ultimately, we really want to be expressing or measuring the risk in percentage of species affected so that we can express our target in terms of a reduction in the risk, okay? Because that relates much more clearly to the goal. So I do apologise for this horrendogram, we would call it, because it's quite horrendous to look at. But nonetheless, I will explain it to you. And it all starts back here with the toxicity data. So we collected a lot of toxicity data from the world, screened it all, etc. The first thing we did was we developed toxicity equivalency factors. And with that information for our 5 key PS2 herbicides, we were able to convert our loads that we're measuring coming out of the rivers out to the reef to diuron equivalent loads. So they take into account the relative toxicity of the chemicals. So we now have changed the targets that we've set for water quality to be in toxic loads, and then every year we report through the Reef report card on progress towards meeting those targets. So that's the first thing we did with this data. The second thing, which is partly what we're here about at this meeting, is about deriving new guideline values. So we used this data that we used here, but a whole lot of additional data as well, to derive guideline values for that list of pesticides that I showed you. Those will then go into the Australian and New Zealand guidelines and separately into the Great Barrier Reef water quality guidelines. When we've got that, that's a nice starting point to do risk assessments. What will come out of that will help us develop what we call water quality improvement plans. But what we're currently doing now is we're taking these SSDs and our guideline values, we're using the MS PATH method, and what we're doing is we're going to be able to convert our toxicity data from every single sample that we have into a percentage of species that are being affected and look at an annual value of that, and that will, in maybe probably 2 years, will probably become our new water quality target. And again, we will then start reporting our progress towards meeting that target in terms of, and that target will be in terms of the percentage reduction of the risk. Now, the current work that we've just published was on the development of the method for the toxic loads, and we actually think we have made some significant improvements to the method for calculating TEFs and TEQs, and that's is online. It actually hasn't gone into the hard copy yet in IEAM, so that's available. And then what we did was we applied this new methodology to data that we had for the Great Barrier Reef, and those results are in that second paper. Now, what I want to show you here is what we're arguing about and how we felt that loads, the mass targets, could be misleading. So here we have just one particular set of years worth of data. These are the loads of pesticides in kilograms coming out from some of our rivers. And it's very clear, hopefully, that you can see that by far the main contributor to the pesticide loads coming out is the Fitzroy River. And by far the most important in terms of the load is tebuthyron. So as a manager, if you were trying to reduce the pesticide loads by to the 60%, I think a lot of them would go, right, we'll target the Fitzroy and we're going to target tebuthyron. Okay? That would be quite a logical thing. Why would you put a huge amount of effort in here to reduce this by 50%? That's not going to make the squat effect on overall. So the logic, you could see it would be very easy for them to focus on that. But when you change it to toxic loads, which take into account the relative toxicity, the picture is completely different. The Fitzroy is no longer really very important. This is a creek, not a river, a creek, so it's really small. Its catchment's only about 300 square kilometres. Small by our standards. But it's one of the major contributors. And some of these other ones, which were really just all had tiny, tiny total loads, when you start looking at it in terms of toxic loads, they become really quite important. And it's no longer tebuthyron, which is the most important driver, it's diron, because it's the most toxic. Now, the other thing that we're starting to do is we're using metagenomics. And this is still in this sort of transition from a sort of an experimental research type approach to getting it to that point where it can be put into a regulatory framework. So with some of the metagenomics work, if you've got a whole lot of different sites with various factors, various stressors, you can use multivariate statistics to try and work out which are the most important stressors, but you can also work out what are the sensitive species in terms of a particular stressor and what are the tolerant species. And you can use the metagenomics to work out at what sort of concentrations you start getting the tolerant species disappearing and the tolerant species dominating. And you can work out a multi-species field-based toxicity threshold. We're probably not going to, in the near future, be starting to say base our guideline values on this, but we would certainly be using this type of data as a confirmatory measure to see if it supports the guideline values that we've done. Or if it doesn't, you could mount an argument in our case, because ours are only guidance, that the value should be changed. Okay? And with that, I'd just like to thank you, the workshop organisers, very much for inviting me here. And of course, I'd like to thank all my colleagues, co-authors and students who I've worked with over the years. Thank you very much.